Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 15 on fluid mechanics for undergraduate students in chemical engineering. Let me begin by briefly recapitulating what we were doing in the last lecture. In the last lecture, we completed nearly the discussion on integral momentum balance, okay, and we also illustrated the application of integral momentum balance through an example, whereby we calculated the force due to a jet that impinges on a solid surface, and we showed how the integral momentum balance can be used to evaluate the force. And there is one further thing that we have to discuss before we complete this topic. Okay, and before we do that, let me first write down the integral momentum balance for your convenience. So, the integral momentum balance for a control volume takes the following form. This is the time rate of change of momentum present in the control volume plus integral rho v dot n dA over the control surface is equal to the sum of all the surface forces and body forces present in the control volume. So, this term is the term that tells you that how momentum changes within a fixed region of space, that is a control volume, and this is the term that denotes how momentum enters and exits the control volume by virtue of flow. So, this is the momentum flux term that enters and exits the control volume through the control surfaces, and these are the surface and body forces. Okay. And we gave several hints or tips as to how to use this for a given control volume, for a given problem. And we also saw in the last lecture number 14, that for the same problem you could choose different control volumes, and as long as you use the correct, as long as you do the steps correctly, the answer will be the same regardless of the choice of the control volume. Having said that, of course, certain control volumes are more easier or more convenient for problems, certain problems compared to others. So, it comes with experience and some judgment as to which is the most appropriate control volume for a given problem. But even if we do not hit the right or the most appropriate control volume, okay, as long as the steps are done correctly, the answer will remain the same, and it is regardless of the choice of the control volume. Okay. Now, there is one thing that you should remember, that whenever we have to evaluate this momentum flux term, it is a surface or area integral. Okay. Now, for example, you could imagine that fluid is entering a simple control volume. Okay, let us demarcate, let us show the control volume using this red line. Let us imagine that fluid comes through here and exits through here. Now, as I have told you several times in the last two lectures, okay, the term, the velocity enters and exits like this. So, v dot n is always negative in the entrance and it is positive in the exit, regardless of the choice of coordinate system, because v dot n is a scalar quantity, it is a dot product of the velocity and the normal to the control surface, and velocity, and regardless of how you choose the coordinate system, velocity v dot n is always negative in the entrance and v dot n is always positive in the exit. Okay. So, once you do that, you have to typically, so let me just focus on the momentum flux term in the integral momentum balance, that appears like this: rho v dot n dA over the control surface. Okay. Now, suppose we assume uniform flow. Okay. If the flow is uniform, then V is independent of the cross sectional area of the control surface. Of the CS. This implies that the velocity is a constant. Okay. So, you can pull this equation will simplify to the following: rho v v dot n integral over C s over all control surfaces dA. Okay. And this is simply now rho times v dot n is essentially, okay, let me just complete this. This is simply equal to summation, and okay, integral over dA is simply A. Okay. Let us focus on, let us say, the inlet part of the control surface. Okay. So, v dot n is minus, let us say, v. Okay. And so, this gives you minus rho v a times the velocity vector. The negative sign is because we are, let us say, we are focusing on the inlet. So, this is also equal to, okay, rho v a is nothing but the mass flow rate m dot times v, the velocity vector. Okay. This, so mass times velocity is momentum, mass flow rate times the velocity, that is the rate of mass entry times the velocity vector, is the rate at which momentum enters the CV through the inlet by virtue of flow. Okay. So, that is the inlet flux term. So, likewise for the exit or outlet, you will find that v dot n. So, this is all evaluated at inlet. So, let us put in, okay, v dot n is plus v. Okay. So, the integral rho v v dot n dA for uniform flow will become rho v v a. This is simply equal to, evaluated at the outlet, m dot times v evaluated at the outlet. So, when the flow is uniform, then we get very simple answers. When the flow is uniform, we get very simple answers for the influx and outflux term. But having said that, we also have to worry about more realistic cases. And let me, before I do that, let me also say that when the flow can be considered uniform. Well, as we saw in the last lecture, whenever you have a free jet, a jet of water that exits into the atmosphere, okay, it is called a free jet, then uniform flow is a very good approximation. Okay. But in many engineering applications, we will see as we go further in the course that you have flow within a pipe. Okay. So, fluid is flowing within a pipe or within a channel, a rectangular channel, okay, bounded by rigid boundaries, okay, surrounded by rigid boundaries. Whenever we have flow through a duct, a pipe or a channel, okay, regardless of the shape of the duct, okay, it is experimentally observed that the velocity is not a constant, it varies with the cross section area. Okay. So, this is an experimental fact, and also when we do differential momentum balances, we will show this rigorously by deriving the equations of motion, the linear momentum balance for a differential linear momentum balance for a very, very tiny control volume. We will show that this can be derived exactly or rigorously. Okay. So, the fact is flow through ducts and channels are not always uniform, in the sense that the velocity is not a constant with respect to the cross sectional area through which the fluid is flowing, and in fact the velocity varies as you go from the center towards the wall, and typically the velocity is 0 at the wall and maximum at the center. So, there is clearly a variation of fluid velocity across the cross section of tubes and channels or conduits in general. Okay. Now, we have to solve problems involving integral momentum balance even with such conduits. Then we are left with evaluating terms of this type, where so let us say the velocity v is given by components u, v, w. Okay. Let us say the flow is in the x direction. Okay. Now, so let us say we are looking at the x component of the momentum balance. So, let us imagine that let us say we focus on the outlet, the flow is in the x direction. So, fluid is flowing in the plus x direction, n is E x. So, v dot n is simply equal to plus u. So, that is what we are looking at. So, we have to evaluate terms like this in the flux term, okay, where u is not a constant, u is actually a function of the cross sectional area. Okay. Now, but so in principle you have to evaluate, first of all you need to know what is u, how is u a function of, let us say we call let us say you have flow in a pipe. If you have flow in a pipe, okay, it is useful to use polar coordinates, where to be on the safer side, to be correct we should call z, okay. So, to be the flow direction z, and then r, and then theta goes, this is called cylindrical polar coordinates. So, theta goes around the axis of the tube. So, let me illustrate this with respect to the Cartesian coordinates which we are familiar with. Suppose you have x, y and z, and let us put a cylindrical tube whose axis is along the z axis. Now, any point, okay, let us keep a tube, this is a cylindrical coordinate system, any point is denoted by, so this is the point, this is the position vector of the point, it is denoted by its projection. First take the projection of the position vector with respect to the xy plane. The distance from the origin to the projection is r, the angle made with respect to x axis is theta, and the vertical z, the vertical projection is z, which remains the same. So, any point is denoted by r, theta, z in cylindrical polar coordinates, and whenever you have flow through tubes, flow through pipes, it is convenient to work with cylindrical polar coordinates, because it simplifies the problem a great deal. Okay. Now, so the fluid is flowing in the, so instead of n calling as E x, n is in the direction E z, because we are using polar coordinates, but let us call the velocity component in the z direction as u, in the z direction. Okay. So, we want to evaluate an integral of this type, rho u squared dA. Now, u is a function typically only of r. Okay. We will see a little later when we do differential momentum balance, we will precisely say when this is valid, but let us now take it as a fact that u is not a function of theta, because the flow is symmetric about the theta, the z axis is called axisymmetric flow. So, the flow is symmetric about the theta axis, it is not varying along the theta direction. Such flows are called axisymmetric flows, and the flow is independent of, so axisymmetric flows means no theta dependence. The flow is also independent of z direction. So, no z dependence, that is the velocity in the z direction is independent of the z coordinate itself. Such flows are called fully developed flows. We will of course discuss these assumptions a little later when we do differential balances. Now, I am just stating it as more like a fact. Okay. So, essentially we have to do integral rho u squared, okay, and where u is now a function only of r. So, let us keep it as u r whole squared. Now, dA is nothing but in polar coordinates, okay, r d theta dr. Okay. This is the area element in the polar coordinates. So, you are integrating r from the center to the radius and theta from 0 to 2 pi. Okay. So, provided given u r, we can carry out the integration to calculate the momentum flux term in the integral momentum balance, because in general the flow is not uniform. So, we have to do this in order to calculate the flux terms. Okay. Now, it will be nice, however, if we can write the integral in terms of a very simple algebraic quantity beta rho a V average squared, where V average is the cross sectional average or velocity. So, V average is defined as integral over, let us say u dA 1 over A, okay, where this beta is called the momentum correction factor. So, instead of evaluating this entire integral, if we can evaluate this once and for all and write it in terms of an algebraic quantity and like the average velocity times a factor that includes for the non-uniform, that accounts for the non-uniformity of the flow, then that will be very, very handy when we do integral momentum balances. So, in order to do this, we have to first calculate what beta is. Now, let me just do this for two cases. One is called laminar flow in pipes, in tubes or pipes, okay, and the other is for turbulent flow in pipes. Now, first of all, I have to tell you what are laminar and turbulent flows. Now, it turns out that fluid flows in general exist in two types of regimes. One is the slow and orderly motion of flow, where fluid elements are nicely flowing past each other, okay, and the flow is usually in one direction, and the flow is steady in the sense that at a given point in space the velocity is not a function of time. Such flows are called laminar flows, okay. And typical example of a laminar flow is, suppose when we try to open a tap, okay, in your house, okay, when the tap is open only very little, okay, you see a very smooth jet of fluid that exits a tap, exits a tap, okay, but when you open the tap fully, then you see that the smooth jet is no longer a smooth jet and it breaks, and it is very, very complicated, the motion is very complicated. So, the smooth jet regime is called the laminar regime in the flow from a tap, and the more when you open the tap completely full, then the more complex flow that exits from the tap is indicative of the turbulent nature of the flow, okay. So, it turns out that the velocity, how the velocity varies with the cross sectional area is very, very different for laminar and turbulent flows. For laminar flows, for which I can give you a full illustration of how to calculate the beta, the velocity in a pipe is parabolic in nature, okay. That is, if I plot the velocity as a function of the radial coordinate, okay, it is a parabola. Velocity goes to 0 at r equals capital R, and it is a maximum, u naught is the maximum velocity at the center, at r equals 0, the center, okay. So, this is both an experimental fact as well as we will illustrate this, how to derive this theoretically or exactly by doing the differential momentum balance a little later in the course, but we right now we will just take it as an experimental fact, okay. While for turbulent flows, okay, the velocity profiles looks very different. So, u is approximately 1 minus r by r to the power 1/7, okay. This is an experimental fact, we cannot derive this rigorously from first principles. So, this we will take it as an experimental fact. This right now, although we take it as an experimental fact, this will be derived later in the course when we do differential balances. So, once you have, okay, once you have the form of velocity, so all you need to do is integrate u squared theta is 0 to 2 pi r is 0 to r d theta dr rho u r squared. Now, once you have come up with this expression, you equate it to beta rho V average times A. Okay. This is all and A is essentially pi r squared for cross section of the pipe. Okay. Now, in order to do that, we have to tell what is V average. We have to first compute what is V average. V average is nothing but 1 over A integral theta is 0 to 2 pi, r is 0 to r, okay, u naught times 1 minus r squared by capital R squared. Okay. So, first notice that, and of course, you have to do the r dr d theta. First notice that the theta, the velocity expression, the integrand is independent of theta. So, you can readily do the theta integral 2 pi by a, okay, times integral r equals 0 to r, and since u naught is a constant, you can pull it out. U naught is the maximum velocity at r equals 0. So, 1 minus r squared by r squared r dr. So, this is 2 pi u naught by a integral r minus r cube by r squared dr. This is 2 pi u naught divided by a, r is 0 to r. Okay. So, this is r squared by 2 minus r to the 4 by 4 r squared, r is 0 to capital R. So, when you evaluate this 2 pi u naught by a r squared by 2 minus r to the 4 by 4 r squared, this is nothing but pi u naught by a, okay, this is V average, okay, pi u naught by a times r squared by 4, okay. So, V average is nothing but pi r squared u naught, okay. So, sorry, there is a factor of 2. So, that will give you pi r, so this 2 will cancel factor of 2 here. So, that will give you pi r squared times u naught divided by 2 a, but a is the area of the cross section of the pipe. So, that is simply pi r squared. So, V average is u naught by 2. Okay. So, we have found that from the knowledge of the velocity profile for laminar flow in a pipe. So, we have to do another integral where you have r is 0 to r, theta is 0 to 2 pi rho u squared r dr d theta is equal to, remember this is the definition of the momentum correction factor, and we want to find what beta is. We want to essentially find an expression for beta. So, to that end we are doing all these calculations. We have a, so V average times a from this expression is nothing but pi r squared u naught divided by 2. So, you write this as beta rho pi r squared u naught by 2, and now we have to do this integral. Again the theta integral is straightforward because it is the integrand is independent of theta. So, r is 0 to r, rho is a constant. So, I pull this out. Now, u is u naught times 1 minus r squared by r squared. Okay. So, this is nothing but so u squared is u naught squared times 1 minus r squared by r squared whole squared. So, you have u naught squared times 1 minus r squared by r squared whole squared r dr. This is the integral we have to calculate. So, 2 pi rho u naught squared, r is 0 to r capital R. Then, so let us expand the square out. So, it is 1 minus 2 r squared by r squared plus r to the 4 by capital R to the 4 times r dr. So, 2 pi rho u naught squared So, let me multiply it through by r squared plus r to the 5 by r to the 4 dr. So, if I integrate this, I get r squared by 2 minus 2 r to the 4 by 4 r squared plus r to the 6 by 6 r to the 4. R is going from 0 to capital R. If I do this, 2 pi rho u naught squared, okay, r squared by 2 minus r squared by 2 again plus r squared by 6. Okay. So, you get these two r squared by 6 will cancel out, and if you see the right side, you have this must equal beta times rho pi, this expression r squared u naught by 2. Okay. So, go back once to see. So, this should be V average squared, because that is the definition of beta. So, that is why we are missing a factor of. So, if you remember the definition of beta, so this is V average squared. So, I missed out a V average factor there. So, we have to write this as V average squared. So, that is why we were missing factor of V average here. So, let me just go back. So, it is V average squared here. So, it is u naught squared by 2. So, this implies, okay. So, you have u naught squared, let us cancel out things, u naught squared will cancel. So, the left side will have r squared by 6 times 2 pi rho, the right squared will have beta rho pi r squared by 2. Okay. So, beta should become, I am still missing a factor of 2 here. Let us just go through the algebra a little bit once again. So, V average is u naught by 2, which is fine. So, let us just look at this term. So, yeah, so there is a factor of 4, because we are squaring V average. So, it is u naught squared by 4, which is why we were missing a factor of 2. So, let us go back here and replace this by 4 and then by 4. So, beta will become simply, so everything will cancel, pi will cancel with pi, r squared, rho. So, beta will become simply 8 by 6 or 4 by 3. So, beta is simply 4 by 3 for laminar flow in a pipe. Okay. So, likewise, we can also, this is the momentum correction factor. What is the advantage? So, whenever you have a problem in which you have laminar flow in a pipe and that connects various equipment, okay, and if your control surface cuts across the cross section of the pipe, whenever you want to calculate the momentum flux integral, all you can do is you can write this as rho beta V average squared. Okay. You can simply times area. Okay. You can simply replace it by this, where beta is 2 by 3 4 by 3 for laminar flow. Okay. Beta is simply 4 by 3 for laminar flow in a pipe. So, that is a simplicity that the momentum correction factor gives us pipe or tube, because otherwise you have to evaluate the integral each and every time when you do the problem. So, I will quickly tell you what is the beta for turbulent flow in a pipe. So, it turns out that for turbulent flow, u is approximately u naught. As I told you, this is more like an experimental fact, it is not rigorously derivable from first principles like the laminar flow expression for the velocity. Nonetheless, the velocity is a function of the radial coordinate, but if you qualitatively sketch this velocity profile, you will find that the velocity is more plug like, okay, in compared to, this is for turbulent flow. If you compare and contrast this side by side for laminar flow, the velocity profile for laminar flow was like this. Okay. So, there is already a huge difference in terms of the nature of the velocity profile. There is a large variation in the laminar flow, while in the turbulent flow you see that except very close to the walls the velocity is almost uniform. Okay. So, you would expect even before calculating the momentum correction factor that the uniform flow assumption is more appropriate for a turbulent flow as compared to laminar flow. So, let us first calculate the average velocity. The average velocity is 1 over a integral u dA is simply r is 0 to r, theta is 0 to 2 pi, okay, u which is this expression times r dr d theta. So, if you do this, which I will not do the algebra fully, the answer you will get is 49 by 60 u naught. So, the average velocity differs from the maximum velocity only by a factor of 49 by 60, whereas if you were to compare it to this is for turbulent flow, while for laminar flow if you see it is half. So, it is 30 by 60. Okay. So, you can see that the variation in turbulent flow is much more, in laminar flow is much more, because the average velocity is only half the maximum velocity, while in a turbulent flow the average velocity is pretty much close to the maximum velocity. That is because the flow is already uniform in the core of the pipe except very close to the walls where the velocity is varying rapidly to 0 at the walls. So, likewise you can calculate momentum correction factor, and you will find that this is just using the procedure above and changing the velocity profile to this, you will find. So, this I will leave it as an exercise for you. So, this is the momentum correction factor for turbulent flow. Okay. So, beta is very close to 1, more close to 1 in a turbulent flow when compared to laminar flow, where beta was essentially 4 by 3. So, in many practical problems, if the flow is turbulent, then it is a good approximation to keep the momentum correction factor as 1, because the errors incurred by replacing 1.020 to 1 is not much, whereas for laminar flows it is always good to use the actual momentum correction factor 4 by 3 when you compute various forces using the integral momentum balance, because indeed the differences are huge when you consider the laminar flow. Okay. So, whenever you have flow through pipes or channels, okay, it is always good to in order to compute the momentum flux term, which is essentially this, okay, you want to be able to write this as let us take one component. You want to be able to write this as rho v average squared beta times the area. So, we can use beta to be approximately 1 for turbulent flow, and beta is exactly equal to 4 by 3 for laminar flow. Okay. So, this is the use of this is the advantage of using the momentum correction factor whenever you have flow through internal flow through conduits such as flow through pipes and so on. Okay. So, there is one more. So, this nearly brings us to the end of integral momentum balance. We will of course use momentum balance a little later in the course as and when we need them, in order to basically compare and contrast the results that we get from integral momentum balance with, let us say, energy balance, which we will do next. So, we will of course use this idea and concept frequently, but this is the at this point I would like to end this, but before I end I will also like to say that the choice of control volume is very critical in the solution of many integral momentum balance problems. The control surface, which is essentially the boundary that separates the control volume from the surroundings, is an imaginary surface. So, the control surface in no way tends to obstruct the flow or anything, it is just in your mind. You are essentially trying to do a balance of various agents through which momentum is coming in, going out, and it is changing. So, the control surface is essentially an imaginary surface. It can cut across rigid things like flanges and so on. Like for example, in the previous problem that we did in the last lecture, you chose a control surface which cut across the hand which is trying to resist the motion of the body. So, control surface is clearly an imaginary construct that helps us in the solution of various integral momentum balance problems. Okay. So, that is something that we have to keep in mind, and whenever you have flow of a jet that comes out of a nozzle, remember that we have to treat the pressure in the jet to be atmospheric to a very good approximation, and if the jet is free and it is exposed to atmosphere, then the pressure inside the jet is the same as atmospheric pressure, and also that the velocity is pretty much uniform in whenever you have flow of a jet. Okay. That is a very good assumption. Okay. Now, now next comes the force part of the momentum balance. There are two components to the forces. One is the two contributions to the forces. One is the body force and the other is the surface force. In this course, of course, we will usually treat gravity as the only body force. Now, the surface forces, as I told you, can be due to pressure forces or viscous shear forces, or due to reaction forces that come through the fact that your control surface is cutting across various solid surfaces. So, you have to take a careful accounting of various reaction forces also, like we saw in the previous example. Now, viscous forces are usually neglected in a first approximation because we do not have a very good knowledge of what the viscous forces are. So, typically the surface forces are thought to be the pressure force alone. Now, another important fact that we saw was that when you want to compute the pressure, okay, it is only the gauge pressure that usually matters, because if your CV is completely surrounded by atmosphere and if there exists a uniform atmospheric pressure across all the boundaries of the CV, that is across the control surface, that uniform contribution to the pressure will not contribute to any net force on the CV through the control surface. So, only the difference between the actual pressure and the atmospheric pressure will matter in any momentum balance problem, and that is of course the difference is of course the gauge pressure. So, usually the gauge pressure is what is important in actually calculating physically important relevant variables such as forces. Okay. So, this nearly completes the integral momentum balance, and we will soon start the discussion on energy balance. So, now we will start our discussion on a new topic. We are going to do an integral balance of energy, and this topic is very important because the use of energy equation is very frequent in many engineering fluid mechanics problems, as we will see little later after we discuss the basics of the integral energy balance. But first things first we have to understand what is the fundamental principle which gives us the integral energy balance. Okay. Just to recapitulate, we started doing integral balances using the Reynolds transport theorem as applicable to a CV control volume. So far we have done two types of integral balances: integral mass balance, which is essentially a statement of law of conservation of mass as applied to a control volume. Okay. And then we moved on to do the integral momentum balance, which is essentially a restatement of Newton's second law of motion as applied to a control volume. We said that Newton's second law of motion is typically is valid only for a system, not for a control volume. So, we had to use the vehicle of Reynolds transport theorem to transform the time derivative with respect to a system to time derivative with respect to a control volume, and this transformation entailed it resulted in fact that there is momentum flux term. Okay. So, the principles, there are underlying principles which lead to the integral balances: the law of conservation of mass, or principle of conservation of mass, which led to the integral mass balance, and the Newton's second law of motion as applied to a system, which led to the integral momentum balance. Now, we have to first understand what is the underlying principle that will give us the integral energy balance, and the answer is it is the first law of thermodynamics. Okay. So, many almost all branches of engineering will have a separate course on thermodynamics, where you will learn the principles and applications of thermodynamics in greater detail. So, I will take only a very few I will do a very brief discussion on the meaning of first law of thermodynamics as it is applicable for our course, which is essentially a course in fluid mechanics, but the principle of conservation of energy essentially comes from first law of thermodynamics. Okay. So, it is important that we understand what is the meaning of first law of thermodynamics. Now, there are two important principles or two important quantities that play a big role in the thermodynamics, that is, one is work, another is energy. Okay. Okay. So, work done the principle or the notion of work is familiar to us from mechanics. Whenever a force acts over a distance, that gives rise to work, right. So, we know this from mechanics. For example, you could have a ball, okay, at the ground level, okay, and let us say gravity is acting below down. So, suppose I apply a force, okay, over a distance, okay, and push this ball up. So, we have done okay, we have done work on this ball by moving this ball over a distance. Okay. So, that is work done on the ball, but what happens to that work done? Well, we have the work done has gone into increasing its gravitational potential energy, because it is now at a higher position h, okay, compared to its initial position, which is 0. Okay. So, this potential energy gained is essentially mgh, and that must be the work done in moving the ball from the ground level to a particular height h. So, this notion of work done and the equivalence of work and energy is very familiar in mechanics. Okay. So, we can change the energy of the ball by doing work done on by doing work on it. Okay. We can also take out work out of the ball, and we can change the energy. For example, if I drop this ball, okay, suppose you place this ball on a plate, okay, so you are moving this ball from ground level to up by doing work on it. So, you are increasing its potential energy. Now, if you drop the ball from this height, of course, it is going to fall freely. Okay. Now, this potential energy which was stored in the ball by virtue of its height, now the moment you tip it off a table, let us say from the edge of the table, it will convert to kinetic energy of motion of the ball. Okay. So, there is energy, kinetic energy of course is energy by virtue of the motion of the ball. So, that is conversion of the potential energy which was there in the ball to kinetic energy, and so when the ball comes, and this kinetic energy can be converted to work by some mechanical device. Okay. So, when the ball again comes to the ground, its potential energy again becomes 0. Okay. So, you can imagine transferring this kinetic energy when the ball collides to some piston cylinder assembly by, so that you can move a piston or something like that. So, that constitutes extracting, that amounts to extracting work from the motion of the ball. Okay. And finally, the ball again comes to rest at the ground level, going back to its original state of 0 potential energy. Okay. So, this is the notion of work energy in mechanics. Now, the question is doing work only, is it the only way to change the energy of the system? Okay. The answer is no, it is not the only way. Okay. Suppose you have a fluid. Okay. Now, I initially insulate it thermally. Okay. I have gas in it. Okay. And I do work by compressing the gas by moving the piston over a distance h. Okay. I apply a force, okay, over a distance h. So, I am doing work explicitly. Now, what will happen to that work? Well, so this piston which was originally here has come here, and you have done work by compressing the gas. Now, let us call this state B and this state as state A, the original state as A and this state as B. So, now the gas is now in a compressed state, okay, and work has been done on the gas, because clearly the piston has moved over a distance h. So, work has been done by you, and so that has resulted in a compressed state of the gas. Okay. Now, for a moment, now I can also, now you can ask the question, what happens to the work done, okay, in terms of energy. Okay. So, here I macroscopically, if I take a ball, okay, of course, if you do work by lifting it up and placing it on the table, you are changing its potential energy, but here it is not clear what energy we are changing, because macroscopically the gas is stationary on the average, it is not flowing, it is in a static it is in a container, so it is static macroscopically speaking, of course. Okay. Now, in the state B also, once you have done work and once you have done given some time for the ball to settle, in the state B also the ball for the gas to settle, in the state B also the gas will be static. So, what has changed from state 1 to state A to state B? Okay. Now, what has changed is the internal energy of the system. This is a new concept, it is not there in mechanics, it is the concept that comes from thermodynamics. Internal energy of a gas or a fluid in general is that part of energy that is stored in the molecular degrees of freedom of the fluid. Okay. So, remember that when we started out teaching fluid mechanics, when we started out discussing fluid mechanics, in the very first few lectures we said that we are going to take the continuum approach, where we are going to completely discard any molecular interpretation or any molecular description of fluid flow. Okay. So, but nonetheless you cannot, in order to take into account, in order to do a proper balance of energy, okay, the first law of thermodynamics says that if you do work on a completely thermally insulated system, okay, and the gas is initially stationary and finally stationary, so there is no kinetic energy of motion, macroscopic motion of the gas. So, what has happened to the work done? It must go into the molecular degrees of freedom of the gas. So, essentially if you think of a very simplistic picture of the gas as a dilute system of spheres which are randomly moving. Okay. Okay. Now, by compressing the gas, you have increased the kinetic energy of motion of the molecules. Okay. And from elementary kinetic theory, which you must have been familiar from physical chemistry courses or physics courses, you know that this translational kinetic energy of the gas is related to the temperature of the gas. So, essentially by compressing a gas and completely insulating the container while you compress, all you have done is to increase the internal energy. The work that you have done has gone on to increase the internal energy of the gas, which manifests as an increase in temperature of the gas, because the temperature is directly related to the kinetic energy of molecules, translational kinetic energy of molecules. So, this is a new concept that by doing work you can not just change the macroscopic kinetic energy or potential energy of an object, but you can also change the internal energy of an object. Okay. Now, the first law of thermodynamics tells you that, so this is also not very different from what mechanics is doing, because mechanics is saying that by doing work you can change macroscopic energy, like macroscopic kinetic energy of the ball or its potential energy. But here we are merely saying that the work that you are doing is going to do something else, that is change the internal energy of the gas. Okay. Now, what is very important is that first law of thermodynamics tells us that that is not the only way to change the internal energy. So, mechanics tells us that the change to, in order to change the energy of the system, you have to do or take out work from the system. But now, the first law of thermodynamics tells you that the internal energy of the system can be changed by merely heating the gas. Okay. And by heating the gas, so imagine, so let us do the following experiment. Initially you had state A, okay, and you have an insulated container, state A, gas, Now, you compress the gas to state B. I argued that the work done in the compression has gone on to increase the internal energy of the gas and therefore, its temperature. Now, remove insulation and expose, but maintain. So, let us say we are compressing using a weight. So, maintain the position of the weight, so that you are not allowing the piston to expand. Okay. So, just remove the insulation. So, what will happen is if you remove the insulation, okay, since the gas in the cylinder inside the piston cylinder assembly is greater than, has a higher temperature than, so T b is greater than. So, initially let us say the gas has temperature T a, same as the ambient outside, but T b is greater than T a. So, there will be, if once you remove the insulation, then since this is at a higher temperature than this, then energy will flow from inside the gas to outside. Okay. Now, I will take the same system, I can bring it back to state B by merely applying heat, okay, to this system. So, I take this system, once I have allowed this gas to reach, by virtue of heat transfer it will lose heat. So, it will eventually reach the same temperature T a. Now, I can bring it back to the same system with temperature T b, okay, by a completely different route. I am just supplying heat by virtue of, let us say, a Bunsen burner or something like that, or an electric heater, whatever it is. I can bring the system back to the same state, okay, state B, by an entirely different route, that is through heat transfer. So, we said that by you can change the internal energy of the gas by compressing it, okay, and not allowing the heat to escape the gas by insulating it, but we can also change the internal energy of the gas by heating it. So, there are two different modes of changing the internal energy of a system. One is by doing macroscopic work on the system, that is like compression, and the other is by supplying heat to the system. So, this is the sum and substance of first law of thermodynamics, and we can mathematically express this as follows. The change in total energy of the system like gas in a piston cylinder assembly is equal to the amount of heat transferred into the system minus the amount of work done by the system. So, in thermodynamics, in engineering thermodynamics at least, this work always involves a sign convention. So, one has to understand very clearly whether the sign convention is work done by the system on the surroundings is positive, or whether it is vice versa. In engineering thermodynamics, it is always taken that the work done by the system on the outside, that surroundings, is positive, while work done on the system by the surroundings is negative. So, that is why we have a negative sign, because if the system is doing work on the surroundings, that is work is done by the system on the surroundings, that means that will lead to a decrease in energy of the system. Okay. So, this is the mathematical representation of the first law of thermodynamics. The change in total energy of the system is equal to the amount of heat that is transferred to the system minus the amount of work that is done by the system. We will stop here at this point, and we will continue from here in the next lecture.